Hello everyone, my name is Rahimi Khojasteh from INRAE. We are at French National Institute for Agriculture, Food and Environment. I would like to talk about particle position prediction based on local Lagrangian coherency in time-resolved particle tracking velocimetry or 4D-PTV. We'll have 9 sections for this talk, and first I will explain quickly the working principle of 4D-PTV and what we have as a predictor function and how we can improve it by adding Lagrangian coherent structures and formulate the prediction cost function. Then we will have 2 synthetic and experimental case studies. In the flowchart of the 4D-PTV, we have basically 4 main steps: IPR, initialization, prediction, and optimization. In IPR, you reconstruct particle position. In initialization, you try to initialize tracklets out of triangulated positions, reconstructed positions, which we proposed Lagrangian Coherent Track Initialization LCTI in the first LPT challenge for this section. And now we talk about prediction. What we saw in the literature was to use polynomial or Wiener filter predictors, and today we would like to see if it is possible to add more physics into the predictor function to make the optimization to have more robust optimization. This process continues iteratively until all the tracks are tracked for the next time step Tn+1. The prediction principle, if I want to say, let's assume we have a couple of particle position histories. Here we have 5. Then you fit a curve over these known positions to extrapolate the next possible position. Then optimization tries to optimize this discrepancy in order to find the true position. What we say with that is that we argue that single particle position history is not enough to predict the particle position in complex regions, especially when you have high acceleration. So what we do is to add local neighborhood information. Velocity and acceleration of your neighborhood information can improve the prediction accuracy. But the question is, what neighbor particle is coherent with your target particle? To answer this question, we proposed using Lagrangian Coherent Structures, LCS, to identify particles, coherent and non-coherent particles. As an example, here is a schematic of 2D turbulent flow. You can see group of neighbor particles, but each group is belong to different cluster of motions. And by time steps, you can see the target particle can especially meet neighbor particles, but not necessarily be coherent. So that's the reason we need to define LCS to identify coherent boundaries, Lagrangian coherent structure boundaries, to be sure that neighbor tracks are coherent with your target track to have better prediction. To quantify the Lagrangian coherent structure boundaries, we use FTLE, finite time Lyapunov exponent. To compute the FTLE value, we need displacement map between each 2 neighbor tracks. So we have vector displacement. The magnitude of this vector displacement can end up with a deformation tensor, which contains information of your rotation between 2 particles, contraction and expansion. And maximum eigenvalue of this deformation tensor can give you FTLE value, which is the parameter that we are looking to find if these gold tracks are coherent and the red ones are non-coherent. And just to point that largest eigenvalue of this tensor eigenvector of this eigenvalue shows the direction of separation. So this is good information we need. So far we can identify coherent neighbor tracks. We use velocity and information of velocity and acceleration information of these neighbor tracks to improve prediction in the formulation part. In this study, we considered 4 predictor functions. DNS predictor, you don't have to minimize anything. You just use velocity of DNS multiplied by the time of your synthetic time step, which is not DNS time step. Then you get final position. Polynomial predictor, you minimize least mean square, and then you predict. Wiener filter, you find your filter parameters for the history, and then shift it by one time step to predict the next step. But what we have here as a coherent predictor, we have 3 terms. We have history, we have terms for the velocity of coherent neighbors and acceleration of coherent neighbors. Therefore, the cost function that should be minimized is combination of history. Here you can see history, velocity, and acceleration. Velocity and acceleration obtained from your coherent motions, history obtained from your target particle. To assess this this cost function, we use synthetic data. The synthetic data we used is based on direct numerical simulation of the cylinder wake flow at Reynolds 3900. We took one subdomain of this simulation and then transported 150,000 particles over this region, and then we started comparison. Just to mention that the data, Eulerian velocity, Eulerian pressure, and Lagrangian trajectories of this data is available in our data link for further studies if you are interested. If we look at the improvements in global view and put the distribution of position estimation error in one plot for each DNS for each predictor function, and also normalize the PDF distribution by DNS predictor. Let's assume DNS predictor is the reference that we have in this case. So you can see, even by knowing the velocity of your ground truth velocity, you still have error of your position because of this term, because your time separation is not exactly your DNS time separation. We normally, what we have in real experiment, our DT is much larger than the DT DNS. That's why we have this distribution. And if you look at this method B, polynomial predictor, which is third order polynomial, you have a high error, and distribution is quite is not narrow. Wiener filter showed better performance, and we showed by using coherent predictor that we can have more accurate estimation by using coherent neighbor informations. And in the instantaneous point of view, if we wanna compare to see what's happening for the estimation error for each time step, here we have evolution over 1000 DNS time step, and we took every 20 DNS time step for the time spacing between two consecutive frames. Let's have a look on the trajectories. You see particle trajectories coming here. We have two shears. We have circulations here. We have complex motions here. And just keep in mind that new interior particles are not considered in this study. So only particles at the beginning are considered for the assessment. And if we project all the estimation errors on one plane in streamwise direction on section B, you can see the evolution of error by time step in different techniques. Well, DNS predictor is supposed to show the best performance, and we can see that, and also it also represents that this is the maximum accuracy that we can get by predictor function, because we cannot go further than DNS velocity. On the other hand, the polynomial predictor, the error is quite clear, and you can see it's shaped by the flow behavior. You have rotation here, you have rotation here as well, and it's highly correlated with the acceleration. Wiener filter showed better performance, and the coherent predictor, if you look at the coherent predictor, it showed more accurate than is the most accurate predictor compared to Wiener and polynomial predictors. And we also showed the other directions, again in the stringwise, but in the other component, x and z component, and you can see still polynomial hits the maximum. The next step, we study. In the experimental study, we try to do the same Reynolds number, the same configuration, but with 4 cameras, and using helium-filled salt bubbles and LED for the illumination. Here you can see the regions that we did for the measurement. We tried to be as close as possible to the cylinder, and we started by almost 4 diameter downstream of the cylinder, and did acquisition for almost 300 centimeter down, starting from 4D to downstream of the cylinder. And if we look at the results we got, first of all, our measurement starts from here, more or less, and you can see we have sheddings convecting downstream of the cylinder, and trajectory reconstruction of this measurement is showing clear signs of this kind of flow behavior. And by the vorticity isosurface obtained by these trajectories, you can see these complex motions. So to do comparison for this study, we try to put aside the optimization part and only focus on the prediction part. So whatever we get after the initialization, so we use that information for prediction assessment. And then we compare the predicted position with the final optimum position. So in this way, we can see, while polynomial predictor is still the worst case scenario, and Wiener filter showed better performance in a real experiment. It's supposed to, by its definition, it's supposed to work better in noisy conditions. So that's why we have better performance in using Wiener filter, but it's still coherent predictor showed outperformed Wiener filter. And if I wanna show the instantaneous flow motions by this experiment, you can see that we have complex flow behaviors and vortex sheddings downstreams of the cylinder. In the conclusion, I would say that coherent predictor is a complementary function in 4D-PTV, so you can use it in complex regions. If you have a complex flow motion, you can use Lagrangian coherent structures to identify your coherent neighbors, and then use those coherent neighbors to improve your prediction accuracy, to be sure that your optimization is robust and you don't get false detection. And at the end, I would like to say that when we do trajectory, when we do prediction for a single particle, we have to keep in mind that Particles are not alone in the flow field. That's why we proposed using LCS to determine coherent motions instead of single trajectory.